This is lesson 8-9, prediction equations. When real-world data are collected, the points graphed usually do not form a straight line, but may approximate a linear relationship. A line of fit is a line that is very close to most of the data points. So in this section, what we'll see are sets of data where the points represent something real, but they typically don't lie on a straight line. You'll basically deal with scatter plots, but typically these data sets can be approximated by a straight line. So we'll draw a line that looks pretty close. In class, we'll actually use our graphing calculators to calculate the best possible line for the data. So this will actually be a fairly short section as far as the video is concerned, because most of what we're going to do will eventually be on your calculator. So, but just to get the concept of what this is, let's take a look at example 1. It says the table shows the number of girls who participated in high school athletic programs in the United States from 1973 to 2003. We are first going to make a scatter plot and draw a line of fit. So what we want to do is get this table of information into this graph. So let's go ahead and plot each of these points. So in 1973, there were 817,000 participants. So, and notice 1973 isn't exactly on here, so, and neither is obviously 817,000. So we're just going to have to get pretty close with this. So, about right there. 1978, 2083, so that would be about right here. 1983, 1780, about right there. 1988, 1850. 1993, 1997, 1998, 2570, and 2003, 2856. Okay. So you can see here that we have a scatter plot. The points are not all exactly on a straight line, but you can see that they are generally trending in a positive direction. So they kind of head in a positive sloping direction. So we're not going to be able to draw an exact line that fits every single point on the graph, but we should be able to draw a line that's very close to those points. So, when you're sketching a line of best fit, not everybody's line will be exactly the same. You basically just want to line up your ruler or the edge of your protractor or whatever straight edge you're using to draw your line. You want to line it up so that it goes about through the middle, or what looks like the middle of those data points. So probably something kind of like that. And we can see how, again, it doesn't hit really any of the data points in this set, but it's about in the middle. There's a couple on one side, there's a couple on the other side, but roughly it goes through the middle of the data. Alright, for part B, we're going to use the line of fit to predict the number of female participants in 2010. So use the line that we've drawn. We'll find 2010, we'll go all the way up here, and we see that it's between 3,000 and 3,500, a little bit closer to 3,000. So halfway between these two would be 3,250, and this is just a little bit below half, so maybe 3,200. And this is in the thousands, so this would be 3,200,000, so 3.2 million. Alright, part C says to write an equation in slope-intercept form for the line of fit. Well, using what we learned in section 8.8, if we have 2 points that are on this line, we can write an equation for it. Well, keep in mind, we want an equation for this line, not necessarily an equation for a line that goes through two of these data points. So what we're looking for are not these purple points that I have sketched here, or that I've plotted. We're looking for points that are on this line. So I see that there's a point right here that's on that line, and a point right here that's on that line. So those are the 2 points I'm going to use. So this point is 1990, 2000. And this point has coordinates, let's see, this is 2000, this would be 2005, 2010, 2015, and 3500. Okay, so let's go ahead and write an equation using those 2 points. So remember, the first thing we need is the slope, y2 minus y1 over x2 minus x1. So let's substitute our y values. Here's y2 minus y1, so 3500 minus 2000. And then x2 minus x1, x2 minus x1. Okay. And 3500 minus 2000 is 1500. 2015 minus 1990 is 25. And you divide those, you get 60. So now we have the slope. The question asked us for an equation in slope-intercept form, so we definitely want it to look like y equals mx plus b. But we now have m, so we can replace that. So we have y equals 60x plus b. But we need to still find out what the y-intercept is. So we'll take one of the points that we have here, and we'll use this first one since the numbers are a little bit smaller. And we'll substitute that into our equation for x and y. So in this ordered pair, y is 2000, so 2000, 60, and then x is 1990. Alright, I'm going to solve this for b. So let's go to multiply these two. 60 times 1990, 119400. And then to solve this for b, we want to get rid of this number here, so we will subtract that. Those cancel, we're just left with b, and 2000 minus 119400 is negative 117400. So this is the value for b. So this goes back up to here and replaces the b in our equation. So y equals 60x minus 117400. Okay. The last part says use the equation from part C to predict the number of female participants in 2010. So remember in part B, we used the line of fit that we had drawn on the graph to predict the number of female participants, and we got 3.2 million. Let's go ahead and do the same thing, but this time we're going to use the equation to predict the number of participants in 2010. So here's our equation. And now the year X will be 2010. Okay, so let's go ahead and multiply these. 60 times 2010. And then we'll subtract. And we actually get the exact same number that we had predicted from our line. And sometimes, and by the way, remember that this is in thousands, so we would still need to add those extra zeros for our actual answer. So 1,000. So we get the exact same number. This doesn't always happen this way. Sometimes what you can read from the line is a little different from what you'll get from your equation, but you'll see much more of that in class, again, when we use the graphing calculator to actually come up with a more precise equation. But you should be able to get at least the basics of what a prediction equation is at this point. Okay, let's move on to section 810, systems of equations. A system of equations is a collection of two or more equations with the same set of variables. Usually for us, this will be x and y, though it could be something different, especially if it's dealing with an actual real-world situation. But two or more equations with the same set of variables. The solution of a system is an ordered pair that is a solution of both equations. So it has to be a solution of both of the equations in the system. For example, the graph at the right shows the graphs of the equations y equals x plus 1, that's this line right here, and y equals 2x minus 2, that's this one right here. The graphs appear to intersect at the point right here, 3, 4. And the scale here is by 2, so that's why that looks like it's not exactly at a whole number, but it's halfway between 2 and 4, so that's 3, 4. Now, it looks like that's where they intersect, but to confirm that this is the solution of the system, we can replace x and y with 3 and 4 in both equations, because remember, if this is a solution to the system, it has to be a solution of both equations. So let's check and make sure it's a solution to y equals x plus 1. We'll substitute 3 for x and 4 for y. So y is 4, x is 3, and this just stays as 4. 3 plus 1 is 4. Those are the same on both sides. That is a solution to the first equation. Let's check it in the second equation. So we're going to replace y with 4, and we'll replace x with 3. So 2 times 3 is 6. Minus 2 is 4. So again, this was a solution in this equation. So this is the solution of the system. It's a solution of the equation y equals x plus 1, and it's a solution of the equation y equals 2x minus 2. Now normally we won't be verifying solutions, we'll actually be trying to find solutions, but this was basically just to show you what it means for something to be a solution of a system. So let's look at example 1. It says solve the system of equations by graphing. So we want to graph each of these equations. We want to graph each of these equations and see where they intersect. So we have the equation y equals 2x. Remember, we can use slope-intercept form. Since this is in slope-intercept form, we can use slope-intercept form to help us graph the equation more easily. So this has a y-intercept of 0, because this is like y equals 2x plus 0. So that's where we'll start. And then the slope of 2, that's like 2 over 1. So rise 2, run 1, we'll go up 2, and to the right 1. And I'll do a couple of these points so that we get a nice, accurate line. Alright, and then we'll connect those to make a nice straight line. By the way, when you're solving systems by graphing, it's very, very important that you plot several points to make your line, and that you use a ruler or some other sort of straight edge to actually connect the dots. Because sometimes if you're freehanding it, your line won't be straight and it'll look like two lines intersecting in one place when they actually intersect somewhere else. So just be careful with that. You want to be as precise as possible if you're going to solve by graphing. Alright, for the second equation, y equals x plus 3. So we'll start at the y-intercept 3. And the slope, the number in front of x here is 1. So the slope is 1. And that's like 1 over 1. So rise 1, run 1. So up 1, to the right 1. Up 1, to the right 1. And this is what we really like to see happen when we're solving by graphing. Now when I go up 1 and to the right 1, I've landed exactly on a point that was on the other line. So we'll still go ahead and connect this to make a line so that we have both lines drawn in our graph. But it's very easy to tell at this point that that is definitely the solution, because using the slope and the y-intercept, we landed on this point for both graphs. So the coordinates of that point are 1, 2, 3, 1, 2, 3, 4, 5, 6, 3, 6. Okay. So for the try it yourself problem, you're going to do the same thing. Both equations are in slope-intercept form already, so you should be able to use the slope and the y-intercept to graph each one and look for where they intersect. So pause the video, graph those two, and come up with your solution, and then press play to check your answer. Okay, here's what your lines should look like. That's 1. And this is the other one. And you should be able to see where they intersect. It's right here. And that is the point -2, 0. Okay. A system of equations can have one solution, no solution, or infinitely many solutions. And you see pictures in this table here to show you what those would look like. So far what we've seen are systems that have one solution. There are two lines that intersect at a single point. So when you have intersecting lines, you have one single solution. And we could actually end up with two lines that are parallel, that never intersect. And if that's the case, they have no solution, because there's no single point that's on this line and on that line. That will never, ever happen. So if the lines are parallel, there's no solution. Sometimes what we end up with are two equations that actually give us the exact same line. Usually one of them is not in slope-intercept form, so that kind of masks that it's actually the same line. But once we actually graph it, we see that they are indeed the exact same line. Well, if this is the case, this system has infinitely many solutions, because think about this. You want a point that's on this line and on this line. If it's the same line for both equations, every single point that's on one line will also be on the other one, because they're exactly the same. So parallel lines don't intersect anywhere. They have no solution. Two equations that give you the same line intersect everywhere. One is right on top of the other one, so they have infinitely many solutions. Okay, let's see what this looks like in an actual example. So example 2 says solve each system of equations by graphing. Same thing we've been doing. Okay, so for the first one, we have y equals 1/2 x minus 1. And again, in slope-intercept form, that's what we really like to see. So let's go ahead and use the y-intercept and the slope to graph this line. So this has a y-intercept of -1. There's that. And then the slope is 1/2. So remember, rise over run. So rise 1, run 2. So up 1, and then to the right 2. Up 1, to the right 2. Remember, do a few points so that your line is nice and straight. Okay, there's the first line. And then the second one is not in slope-intercept form. So we've got a couple options here. We could try to solve this for y to put it into slope-intercept form, which is actually kind of difficult. Or we could try to graph it by creating a table of values. Specifically, remember the two values that really make things easy for you are finding the intercepts by substituting 0 for each variable. So let's go ahead and do that. let's make a table. And for the first one, let's put in 0 for x. When you put in 0 for x, you have 0 minus 2y equals 2. Well, 0 minus 2y, the 0 just goes away. This is just negative 2y equals 2. And to get rid of this negative 2, we'll divide. And we get y equals negative 1. So one of the points that's on this line is at 0, negative 1. Hey, weird. That's probably the point we're looking for. But we have to keep going because remember, we could have infinitely many solutions if they're the same line. So let's find one more point. We found the y-intercept. Let's go ahead and find the x-intercept. We plug in 0 for y. And now, when we plug in 0 for y, we have x minus 2 times 0 equals 2. Well, 2 times 0 is just 0, and x minus 0 is just x. So we get x equals 2. So another point on this line is the point 2, 0, and that is, right there. So now when I go to graph the second line, notice it's the exact same line as I already have drawn. So these two equations gave us the same line, which means our answer, since it says solve each system, the solution is not same line. The answer is infinitely many solutions. If you get confused trying to remember which one is which, again, think of it this way. When we found this solution that worked in the second equation, it was already on the other line, which means it was also a solution of this equation. When we found the second solution for the second equation, again, it was already on the line that represented the first equation. So right here, we found two solutions to both equations, and that's not possible to have only two, so it has to be infinitely many. That's just another way to look at that. Alright, let's do one more together. So this one says y equals 2x and y equals 2x minus 4. So again, slope-intercept form makes things easy, so we'll add that plus 0 just as that placeholder, so that goes through the origin. And the slope of 2 is up 2 and to the right 1. We'll draw a couple points to make sure we get a really good line. Okay. And the second equation is y equals 2x minus 4. So this has a y-intercept of negative 4 and a slope of 2. So we'll go down to negative 4, and then we'll use our slope of 2 to find more points. So again, rise 2, run 1, up 2, to the right 1, up 2, over 1. Okay. Now, what you should see from these two lines is that they are parallel. And if we wanted to double check that to make absolutely certain, we would want to make sure that they have the same slope. And, well, you can see that right there from the equations. They both have a slope of 2. You can see it from the graph also, up 2 over 1. This is also up 2 over 1. These have the same slope. They are parallel lines, which means that this system has no solution because there's no single point that is on this line and also on this line. There's no single point no single ordered pair that's a solution to both. Okay, there are two try-it-yourself problems for you to attempt. You're going to solve each one by graphing, and again, be aware of those possible kind of unique sort of situations, infinitely many solutions and no solutions. So pause the video, solve each of those by graphing, and then press play when you're ready to check your answer. Okay, for the first one, your lines should have looked like this for the first one, and like this for the second one. Well, those are parallel, so that is no solution. For the second one, y equals negative x minus 3, and 2x plus 2y equals negative 6. When you graph the first one, get a line that looks like this. And then hopefully for the second one, you tried to graph that using the intercepts and not by trying to put that into slope-intercept form. This one's, again, kind of difficult to do that with. But if you graph that by intercepts, you would have noticed that they have the same x and y intercepts. So these are the same line. That means that this is infinitely many solutions. Okay, last thing to talk about for systems of equations. Sometimes it is not really the best way to solve a system by graphing. You can think about, let's say the solution were not whole numbers or not integers. What if the solution was 1/2 and 2 3/5? You would not be able to tell that from the graph. Most of the graphs that we deal with do not have that level of precision. You're not going to graph that detailed to be able to tell exactly where it is. So in that case, we need some sort of algebraic method in order to actually find the solution. The same thing is true if you were talking about a very large set of numbers. So maybe something that was more similar to something you might see in the real world. Even thinking back to, this wasn't a system, but in the lesson we just looked at, lesson 8-9 with the prediction equations, we had year graphed along with numbers of participants in the thousands. Those are very, very large numbers. And if you had to graph two lines where those on a graph with numbers that large, it can become very, very difficult to figure out exactly where that solution is because the numbers are so big. So we do need some sort of an algebraic method to solve a system, and that's where this method substitution comes in. It's exactly what it sounds like. We are substituting something from one equation into the other equation. And some of these substitution ones will be very straightforward and very simple, and others will be a little more tricky, but the ones that we'll see at this level are still pretty basic. So you'll see in example 3, solve each system of equations by substitution. Well, this first system, the first equation we have is y equals 2x minus 5. The second one is very helpful. It tells us y equals 7. There's no x involved in this equation. This is very, very simple. So if y is equal to 7, I know I can replace the y in the first equation with what it's equal to, which is 7. So now I can replace that so it says 7 equals 2x minus 5. And now we learned how to solve these equations a long, long time ago, so we should know exactly what to do here. So let's add 5 to both sides. And then we'll divide by 2. Okay. Now remember, the solution to a system is an ordered pair. So be careful with looking at this and seeing, oh, x is 6. That's not the solution to the system. X is 6 and y is 7. So our solution is the ordered pair 6, 7. Okay, let's look at the second one for example 3. This is very similar, except here, instead of having y equals a number like we did here, we have y equals 2x. So not quite as straightforward, but still very, very, very similar. So the idea is still the same. We can take this equation that shows us what y is equal to, and we can take that expression and replace the y in this equation with 2x. So we have 3, and in parentheses 2x minus 2x equals 20. Alright, let's go ahead and multiply these. 3 times 2x is 6x. And now we have like terms over here. 6x minus 2x is 4x. And the last step, we will divide by 4. 20 divided by 4 is 5. Okay, now remember again, the solution to the system is an ordered pair. It has to have an x and a y coordinate. Well, unlike the previous example, where we knew already what y is, here we don't. All we know is that y is equal to 2x. But if we know x, we should be able to find what y is now. So we will take this value and go back up to this equation that we substituted. And we'll substitute 5 in for x to figure out what y is. And 2 times 5 is 10. So we have an x value of 5 and a y value of 10. So the ordered pair that represents the solution to the system is 5, 10. Okay. There are 2 at the bottom of the page for you to try on your own. You're going to solve these by substitution. So you're substituting a value into a value or an expression into one equation, and then solve it for the remaining variable. Don't forget that your answers need to be ordered pairs. So pause the video, answer those 2 questions, and then press play when you're ready to check your answer. Okay, for the first one, should have gotten a solution of 1, 5. And for the second one, your solution should have been 4, 4.